Hello everyone, thank you for your presence. My name is Nathan de Macedo Silva. I am an electrical engineer and a master's student at the Federal University of Campina Grande in Brazil. Today, I present this work titled SolarVirt Virtual Reality Platform with Artificial Intelligence for Training in Photovoltaic Systems. This work was developed by me along with Ives Reis and Professor Jalbert Araújo and Washington Neves. The focus of the research is to show how we can combine immersive technology with intelligent algorithms to improve safety training in electrical engineering. Let's begin with the context. We know that the global transition to sustainable energy is driving a massive installation of photovoltaic systems worldwide. However, the systems are not just about installation. These require standardized inspection to validate their safety and performance. Specifically, the standard IEC 62446 1. Define the mandatory commission, tests, and documentation. Technicians must be prepared to follow these rigorous standards to ensure the system operate correctly. This brings us to the motivation for this work. The expansion of the solar sector creates a high demand for skilled professionals. However, training these professionals on real live systems presents several challenges. First, there are risks. Working with energy system involves the danger of electrical shock and often technicians must work at height. Second, there are limitations. Physical training was time limits and special constraints. You cannot always take a roller class to the high voltage substation. Therefore, we see virtual reality platform as a complementary strategy. These allow trainings to practice procedures without the physical risks associated with energy equipments. Based on that, your proposed solution is a SolarVirt. SolarVirt is a virtual reality simulator designed to mitigate these risks. But we wanna go step further. We measure virtual reality with artificial intelligence. By doing this, we created an intelligent tutor. This tutor serves to enhance the learning process. It combines the immersion of VR being inside the plant with the accessibility of information provided by AI. Our objectives were defined as follows. The general objective was to design a virtual reality environment specifically for operational training and diagnosis of photovoltaic system. To achieve this, we established three specific objectives. 1. Construct a realistic virtual scenario of a photovoltaic plant. Structure the VR interaction to simulate real system tests like current measurement and implement an intelligent tutor based on artificial intelligence to assist the user. Move on to the methodology. We divided the development process into three main blocks: as shown in this diagram. First, on the top left, we have the development of the VR environment and 3D modeling. This is the virtual part. And second, on the bottom left, we have the integration of the intelligent tutoring based on AI. This is a large part. Finally, these two blocks converge into the implementation of the integrated system, which is the final software running on the headset. For the 3D modeling, we utilize SketchUp and the 3D Warehouse library. We modeled the photovoltaic plant and the substation details to ensure they looked technical and realistic. Then we imported this model into Unity. Unity is the game engine where we build the environment. Here we wrote the scripts that define how the object functions. For example, how a cable reacts when you touch it, or how the physics of the movement works. For the artificial intelligence component, we used the Gemini 2.5 API. The flow works like this. User input collection. The user types a question inside the VR environment. Request formatting. The system packages this question and signs into the cloud. AI processing. The Gemini model processed the question. We used domain contextualization, meaning we give the AI specific technical standards and operation manuals so it answers as an expert engineer, not a generic bot. And the response, the answer, is sent back, parsed from JSON, and displayed on the user screen inside the VR environment. Regarding the hardware, we used the Meta Quest 3 headset. We chose this device because it allows complete freedom of movement. It generates an APK file directly from Unity. The controls were mapped to be intuitive. The right controller is used to walk and turn 316 degrees. The left controller is used to select items, pick up tools like the clamp meter, and activate the smart tutor, for example. On this slide, you can see the application interface. On the left, we have the main menu with the two training modes. On the right, the video shows the system in operation. Note that the headset viewer is mirrored on a smartphone, which allows for external monitoring. In the video, the user starts by inspecting the photovoltaic panel in the external area. Then the user walks into inverter house. This transition demonstrates that by navigation is intuitive. In the video, we demonstrate the interaction in real time. First, the user is in an inverter house. When pointing the controller at the inverter and clicking the trigger, an information box opens. This window provides a detailed explanation of the equipment operation principles. Then the user uses the joystick to out to the solar plant. By repeating the action on a photovoltaic panel, a new window appears displaying the technical characteristics and the modules. This proves that the system effectively links theoretical information to the visual object. On left image, the user measured the first string. The clamp meter shows 8.79 amperes, which represent the nominal current. This indicates that the specific part of the system is working correctly. However, on the right, when the user measures a different string, the reading drops to 0 amperes. This indicates a fault, such as a disconnection or a damaged cable. The important point here is that SolarVirt guides the user through this process. The simulator teaches the student to interpret these values, helping them understand why the current is missing and how to identify the root cause of the problem. This video shows the measurement process in action. Notice how the user pick up the clamp meter and position it around the cable. The user measures on string, check the value, and then move to the next. This repetition helps build muscle memory and procedural understanding. The user learns that they must measure at string individual to validate the entry system. Finally, we have the AI integration results. Sometime during training, a student might have a theoretic doubt. Instead of stopping the simulation to check a manual, they can open the Smart Tutor. In this video, the user asks, what is hotspot in solar panel? The question is sent to Gemini API and the answer appears in the text box. This provides immediate cognitive support, keeping the user immersed while solving their technical doubts. To conclude, SolarVirt successfully validated the technical integration between virtual reality and artificial intelligence. The platform unifies procedural practices with informational support. The AI provides immediate assistance without breaking the immersion. Most important, the simulation enables the development of diagnostic competence without electrical risks. We believe this approach can significantly contribute to the training of the future workforce for the solar energy sector. Thank you very much for your attention.